Okay, today we're going to do discussion 1-1, stoichiometry and limiting reactants. Okay, so first, before we can do that, we have to talk about the mole. A mole is a word that represents a specific number. Now, we have other words that represent specific numbers in the English language. For instance, a dozen, is equal to 12 units. Now, it doesn't matter what kind of units we're talking about. You could have a dozen eggs, you could have a dozen pieces of paper, you could have a dozen chemistry students, and in each case you would have 12 of those particles. Also know that a pair is equal to 2 particles. Now a mole is similar, just represents a different number. And that number is 6.02 times 10 to the 23rd particles. That means 1 mole of anything consists of 6.02 times 10 to the 23rd particles. Now, if we know the number of moles of a substance, we can also calculate its mass using the molar mass found on the periodic table. So if I wanted to look at 1 mole of aluminum, I know that 1 mole of aluminum is going to consist of 6.02 times 10 to the 23rd atoms of aluminum. And if I want to find out the mass of 1 mole of aluminum, I just have to look at my periodic table. So on the IB periodic table, we find aluminum, and we see that it has a mass of 26.98 grams. That means that 1 mole of aluminum atoms has a mass of 26.98. And we can do the same thing with a compound as well, like water. And we know that elements are made up of atoms and compounds are made up of molecules. So 1 mole of water will be 6.02 times 10 to the 23rd molecules. Now, to get the mass of 1 mole of water or any compound, we have to look at the periodic table and add up the masses of each of the atoms in the compound. So we see that water has 2 hydrogens and 1 oxygen. So I'll take the mass of hydrogen and double it and add it to the mass of oxygen to get a molar mass of 18.02 grams. Now we can use these relationships as conversion factors in dimensional analysis. If you're unfamiliar with dimensional analysis, you should have done your summer assignment. You can go to my video and the Chem 1 playlist on dimensional analysis. All right, so here's an example of a conversion. It says a solution needs to be prepared in the lab. The solution requires 2.80 times 10 to the 22nd molecules of quinine. How many grams of quinine should the lab tech weigh out and make the solution? So take a moment and pause the video, see if you can work this one out on your own. All right, so we're going from molecules to grams. Now I know that I can use the Avogadro's number relationship to convert molecules into moles. Then I can use the number of moles, to calculate the mass of the substance. Right. Sometimes we're going to need to use more than one step in our conversion. Since I'm going to go from molecules to moles to mass, I'm going to have a fence with 3 steps in it. So the first thing we'll do is input our given quantity. Now first I'm going to convert molecules into moles, so I'll use the Avogadro's number conversion factor that says that 1 mole of anything equals 6.02 times 10 to the 23rd molecules. Now if I did the math now, we would see that molecules would cancel out and I'd be left with moles. So my answer would be in moles. Since I'm asked for grams, I need to do one more step. So now I'm going to use the molar mass conversion factor for quinine that says that 1 mole of quinine is equal to 324.46 grams. When I plug in the numbers, before I plug the numbers into my calculator, I want to make sure that all my units cancel out except for the one that I'm asked to find. So I see that molecules and molecules will cancel, moles and moles will cancel. The only unit that doesn't cancel is grams, which is good because that's what I'm trying to find. And when I do, I see that this sample weighs 15.1 grams. All right, so percent composition. The percent composition of any compound is the percent by mass of each element in the compound. And it can be represented mathematically like this. The mass of the element times 100 divided by the mass of the compound. Part over the whole times 100. Now if we know the percent composition of a compound, we can very, very easily calculate its empirical and molecular formula. Well, what the heck are those things? The empirical formula is the simplest whole number ratio of atoms in the compound. You could also say it's the simplest whole number ratio of moles of atoms in a compound. And the molecular formula is the actual number of atoms in the compound, and it'll always have the same ratio of atoms as its empirical formula. Let's go ahead and see how we do that. First, let's find the percent composition of calcium in calcium phosphate. So the first thing you're going to need is the formula for calcium phosphate. So calcium phosphate is Ca3PO4 sub 2. So to find the mass of calcium, I'm going to have to take the mass of calcium and multiply it by 3 because there's 3 calcium atoms in that compound, in that molecule. And I'll multiply it by 100 and divide by the mass of the whole compound. Part over the whole times 100. So when I plug in my numbers, I get the mass of calcium from the periodic table, multiply it by 3 by 100, and then divide by 310.18, and I get 38.76%. All right. This problem says the compound is 40% carbon, 6.67% hydrogen, and 53.3% oxygen. It has a molecular mass of 180 grams. What is the molecular formula? Okay, so if we look at this problem, we're not given any specific amounts of the compound. All we're given is percentages. And we know that a group of percentages will always add up to 100. So I can assume that I have 100 grams of this compound. If I have 100 grams of this compound, that means I have 40 grams of carbon. And if I divide by the molar mass, I'll get the number of moles of carbon. I could do the same thing for hydrogen and the same thing for oxygen, and I have all the moles of carbon, hydrogen, and oxygen. Now remember that the empirical formula is just a ratio of the moles of each element in the compound. So all I have to do is get the ratio between the moles of carbon, hydrogen, and oxygen, and that will give me the empirical formula. So to get a ratio, you probably remember this from math, but just in case you don't, you find the smallest number in the set, and you divide all the numbers in the set by that number. So 3.3 divided by itself is 1, 6.6 divided by 3.3 is 2, and 3.3 divided by itself is 1. So that means in my formula I have 1 carbon, 2 hydrogens, and 1 oxygen. So my empirical formula is CH2O. Now this example worked out very, very neatly. I have a whole number ratio, so I'm ready to go. Sometimes you're going to get a 0.5 in your ratio, like 1.5 or 2.5. So we have to come up with a way to, we have to come up with a way to maintain the ratio, but also make all the numbers whole numbers. Well, if you have a set of numbers, you can get the ratio between those set of numbers. And if you multiply all the numbers in that set by the same number, you'll maintain the ratio, but you'll change the value of the numbers. So if you have any number that's a 0.5, if you multiply it by 2, you'll make a whole number. 1.5 times 2 is 3, 2.5 times 2 is 5, etc., etc. So if you get a ratio with a 0.5, if you multiply all the numbers in the ratio by 2, you'll get whole numbers with the same ratio. So now I have to figure out what the molecular formula is. Now to do that, I have to look at the mass of the empirical formula. So if I have an empirical formula and I double all of the coefficients, I'll be doubling the number of each atom, so I'll double the mass. If I triple all the subscripts, I said coefficients, I meant to say subscripts. If I triple all the subscripts in the empirical formula, I'll triple the mass. So I have to see how many times bigger the molecular formula is than the empirical formula. So that I'm going to add up the mass of the empirical formula. I do 12 plus 2 plus 16 for carbon, 2 hydrogens, and oxygen, and I get a mass of 30. So my molecular formula is 180 grams, which is 6 times greater than 30. So I have to take all the subscripts in my empirical formula and multiply them by 6. So my molecular formula becomes C6H12O6, or the formula for glucose. Okay, moving on, stoichiometry. So stoichiometry means using a balanced chemical equation to convert one unit into another unit. So you'll be asked, you're starting with this many grams of this substance, how many grams of the other substance will form? So to do this, we're going to follow the same steps every time. First, in order to do stoichiometry, we need a balanced equation. Once we have a balanced equation, we'll convert whatever we are given into moles, if needed. If the given quantity is already in moles, we can skip that step. Next, we're going to use the mole ratio found in the balanced chemical equation to convert from the given substance to the desired substance. Finally, we're going to use that number of moles to convert to whatever we're asked to find. So let's look at an example. Detonation of nitroglycerin proceeds as follows in the reaction below. If a sample containing 2 milliliters of nitroglycerin, which has a density of 1.592 grams per milliliter, is detonated, how many grams of nitrogen gas are produced? Okay, so we're given an amount of one substance, and we're asked how many grams of another substance will form. That's what you need to see to recognize a stoichiometry problem. So the first thing we're going to do is convert what we are given into moles. Well, I'm not given grams, but I am given volume and density. And I know if I multiply the volume times the density, I can get the mass. So in my fence, I'm going to go ahead and do that. Now, if I stop my calculation now, milliliters would cancel and I'd be left with grams. So the next step is going to be to convert that amount of grams into moles using the molar mass of nitroglycerin. Once I have moles of nitroglycerin, I'm going to use the mole ratio to convert to moles of nitrogen. So I see here in my balanced equation that I have 4 moles of nitroglycerin for every 6 moles of nitrogen. So in my conversion factor, I'm going to use 4 moles of nitroglycerin down below and 6 moles of nitrogen up above. Now, if I started my calculation now, I would be calculating the number of moles of nitrogen that I have. But I'm asked for grams, so I'm going to use the molar mass of diatomic nitrogen to finish the calculation, and I get 0.589 grams. All right, limiting reactants. So methane undergoes combustion according to the following equation. If you have 2 moles of methane reacting with 3 moles of oxygen, which will run out first? So take a moment and see if you can work this one out on your own. Okay, so I see in the equation that the mole ratio between methane and oxygen is 1 to 2. That means that each mole of methane needs 2 moles of oxygen in order to fully react it. So if I have 2 moles of methane, I would need 4 moles of oxygen to fully react it. Since I have 3 moles of oxygen, the oxygen is going to run out first. That makes oxygen the limiting reactant. All right, so how do limiting reactants impact the amount of product made in a reaction? All right, so the limiting reactant will actually determine how much product you're expected to form, and we call that the theoretical yield. All right, so the reason that the limiting reactant determines the amount is because once the limiting reactant is gone, all products stop being produced. For example, if I have 10 chocolate chips, a huge bag of flour, all the vanilla extract I could ever need, all the baking soda I could ever need, and I wanted to make cookies. If I want to put 5 chocolate chips in each cookie, that means I can only make 2 cookies. Once the chocolate chips are gone, I can't make any more chocolate chip cookies. So the chips are going to determine the amount of cookies that I can make. Now, to determine which reactant is limiting, you're going to have to do 2 stoichiometry calculations, one for each given quantity. Whichever one produces a smaller amount, that reactant is limiting, and that smaller amount is the theoretical yield. A little cut here, I just had some of my HL kids come in and distract me. Okay, so here's an example. Pause the video, take a moment, see if you can work it out. All right, the problem says how many moles of bromobenzene is formed when 0.512 moles of benzene react with 0.407 moles of bromine, and how much of the excess reactant in moles remains. And so we already have our balanced chemical equation, so we're going to go ahead and perform our 2 stoichiometry calculations. I'll start with benzene. I have 0.512 moles, and the mole ratio between benzene and bromobenzene is 1 to 1, so that means I'm going to produce 0.512 moles of bromobenzene with that much benzene. Now I'll do the same calculation, but for bromine, I have 0.407 moles of bromine. Again, the ratio is 1 to 1, so that much bromine will produce 0.407 moles of bromine. Because 0.407 is a smaller number, that is going to be our theoretical yield, and bromine is our limiting reactant. So now we have to calculate how much excess remains. Well, the key is to understand what we're doing in stoichiometry. If you know how much of one product forms, then you can calculate easily how much of another product was used to create it. So we're going to work backwards from our theoretical yield to determine how much benzene was used. So I produced 0.407 moles of bromobenzene. Again, the mole ratio is 1 to 1. That means I used 0.407 moles of bromobenzene. Since I started with, that should just say benzene. All right, anyways, I started with 0.512 moles of benzene, so I'm going to subtract what I used, and I'll get the remaining amount. All right, finally, percent yield. Percent yield tells us how well we did in our lab, the efficiency of our reaction. So mathematically, the percent yield is the experimental yield times 100 divided by the theoretical yield. Now, the experimental yield is what we actually gain, what we actually perform in the lab experimentally, which is why it's called the experimental yield. All right, so in the example we did on example 4, if I actually produce 0.396 moles in the reaction from example 4, what's the percent yield? All right, so we're going to use our percent yield formula. So the experimental yield is the one that we got in the lab. So I'm going to take 0.396, multiply it by 100, divide by the theoretical yield, and that'll give me a percent yield of 97.3. And that is it for discussion 1.1. Please, 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 please make sure you are versed in this because it's basically the entirety of Unit 1.